So what I want to talk about is the statistical mechanics of turbulence, which I want to explain to you why I want to do that. But the first thing I want to do is mention that some of this work I'm going to tell you is new, or at least recent. And so my collaborators in the various parts of the work I'm going to talk about, you'll see why, the transition to turbulence and then the fully developed turbulence. So these are my collaborators. Hongyan Shi, who is now the Academia Sinica in Taiwan, Songlin Si, who was an undergraduate here at the University of Illinois and is now a graduate student at Princeton, Pinaki Chakraborty, who was a student here at Illinois and is now on the faculty at OIST, the Okinawa Institute of Science and Technology, along with Gustavo Joya, who is also there. Hamid Kelly is in Bordeaux in France. Tao Tran is in Singapore. And I'm afraid Walter Goldberg passed away a year or so ago, so he's no longer with us, but he was involved in the experiments that I'll tell about later. Okay, so here's what I propose to discuss. And let me, before I do anything else, let me remember to put on my timer, because while we were getting set, of course, I forgot to do that. And so I'm going to set it so I don't. All right, so now we're all set. So I want to tell you a little bit about the philosophy of this, why turbulence has got anything to do with statistical mechanics. And of course, it's impossible for me to talk about statistical mechanics without also mentioning the renormalization group. So I'm going to say something about that. And I want to spend quite a lot of time talking about what is the big question we want to answer, particularly in today's lecture. Because what I find is that you'll see lots of lectures and tutorials on turbulence, and they'll more or less cover the same sorts of things. But I think it's a good idea to think about what the question really is, and then one can see why there is a connection to statistical mechanics. Now, the other thing is that turbulence is often said to be the last great unsolved problem of classical physics. And so I want to also explain why turbulence is really hard. And in fact, I will relate it to problems in phase transitions. So we'll talk about that. So this will be perhaps half of today's lecture. And then what I'm going to talk about next is I will talk about the transition to turbulence. I don't expect to finish that today, but we'll do much of it today. And then tomorrow we will finish that and then talk about fully developed turbulence, and in particular the connection between fluctuation, dissipation, and turbulence. Now, there's extra things that you will learn from these two lectures, hopefully. One is, of course, how to think of turbulence in a new way. The other thing is I want to say something about what you might call similarity methods. So I want to, I'll say, make some comments about that, because that really does connect turbulence to statistical mechanics. I also want to talk about how to use computer simulations to make discoveries and to drive analytical work. And I'll explain why I think that's a pertinent thing. So when we think about doing physics, one of the messages I want to give to you is that we have to make choices about the way we ask questions and the tools that we use to answer those questions. And they're not always obvious about how to do that. And then lastly, you're going to see that in the stuff that I'm going to talk about, particularly today and early part of tomorrow's lecture, there's a lot of really weird transdisciplinary research. We'll see that turbulence is connected to problems not just in statistical mechanics, but in high energy physics and even in population biology. And it may sound weird that this happens, and it is, and it's unexpected, but so you'll get some flavor of how thinking about things in a broad way can make progress. Okay, so let's talk about the propaganda. And I want to start with Richard Feynman, because it's almost obligatory to have some slide about Richard Feynman when one talks about physics. So this is Richard Feynman's Feynman Lectures on Physics, and this is volume 2, where he first introduces the equations of fluid mechanics. I will say something about the equations of fluid mechanics, but not as much as you might think, because one of the odd things about turbulence is that most of what we know about it doesn't really come from the Navier-Stokes equations. So anyway, back to Feynman, as shown here. So what he writes is this, and I want to just quote from Feynman. He's talking about how we've written down the equations of water flow. From experiment, we find a set of concepts and approximations to use to discuss the solution, vortex streets, turbulent wakes, boundary layers. But when we have similar equations in a less familiar situation, and one for which we cannot yet experiment, we try to solve the equations in a primitive, halting, and confused way to try to determine what new qualitative features may come out, or what new qualitative forms are a consequence of the equations. Now think about that. I'm sure you all know who Richard Feynman is. He developed the renormalization theory for quantum electrodynamics, and he won the Nobel Prize for that. That is a theory, the unification of quantum mechanics and electricity and magnetism, that really is our most accurate physical theory. It makes predictions that go to, I don't know, something like 10 decimal places, and you can do the experiments and it all works. So Feynman was somebody who loved to calculate and was the archetypal physicist who likes to calculate and get things quantitatively correct. But what he's talking about here is not quantitative correctness, but qualitative correctness. And this is very important. What he's saying is, not only do we not know how to calculate the solutions, we have no idea what the solutions even look like. And then he goes on to say this: the next great era of awakening of human intellect may well produce a method of understanding the qualitative content of equations. Today we cannot see that the water flow equations contain such things as the Barber-Pole structure of turbulence that one sees between rotating cylinders. Today, well, then he talks about Schrödinger's equation, frogs, musical composers, morality. I don't have too much to say about that, but his point is that we want to understand the types of solutions, not just what they are. Now, when you think about the equations of fluid mechanics, and you want to understand the qualitative behavior of matter, that is what we call statistical mechanics. That's exactly what the goal of statistical mechanics is, to understand the qualitative behavior of matter. What we call this in statistical mechanics is the phase diagram. You give me a Hamiltonian, I will grind away and compute things using statistical mechanics methods, and I will be able to tell you about the phases of matter and about the phase transitions between those phases. And that's what we mean by qualitative content. So when we want to understand the qualitative content of the equations of fluid mechanics, that means understanding the phase diagram of fluid flow. And as I'm going to show you, not only can we understand the phase diagram, we see that there are universality and scaling laws that arise, just like they do in equilibrium statistical mechanics. Okay, so this is a very ambitious goal, and it's certainly not yet, by any stretch of the imagination, complete, but we have made a start. And the things I'm going to tell you about will be the transition to turbulence and about fully developed turbulence and fluctuation and dissipation relations. Okay, so let's get started by thinking about what we do when we do statistical mechanics. We start off with many particles bouncing around in a box, and we know that those particles are obeying deterministic classical mechanics. And if you've ever tried to simulate this using molecular dynamics, as I hope some of you have, what happens is the particles collide with each other, they collide with the walls, they bounce around in some crazy stochastic way. And if you try to measure the pressure or anything like this, you find that they obey, properly averaged and so on, they obey the laws of statistical mechanics. So the deterministic classical mechanics of many particles in a box actually ends up obeying statistical mechanics. So because of the motions around it. So when we now talk about an infinite number of particles in the box, well, an infinite number of particles in the box is a fluid, it's a field, and that obeys classical equations of motion, which are Newton's equations. But when you write them down for a field, for a fluid, then you get the equations shown here, the Navier-Stokes equations. And these equations, I'm not going to say too much about them. This one here, div u is equal to 0, just tells you about incompressibility. This is the advective derivative that just says mass times acceleration is equal to the force on the right-hand side. And this is now for the little volume element, and so this is the mass per unit volume, and this is just the term that comes from following an element as it moves with the flow. The fact that this term here is nonlinear is what makes the problem hard. It's only a quadratic nonlinearity, but it's absolutely terrible what the effects of it are. Now, the important thing is this. This is really just an infinite number of particles bouncing around in a box. And so it shouldn't be a surprise that statistical mechanics applies to a fluid as well. But that's not normally how it is thought of. Okay, so let's talk about the phase diagram of turbulence. And so the way I want to do that is I want to write down an axis which is a control parameter, and the control parameter is typically called the Reynolds number. So u is a characteristic velocity, L is a characteristic dimension, such as the diameter of a pipe, and nu is the kinematic viscosity, which is the regular viscosity divided by the fluid density. And so this Reynolds, this number, when you rescale these equations, the only number that comes in is the Reynolds number, and it comes in front of this del squared u term, which is comes in as a 1 over Reynolds number term. Rho disappears, mu disappears, you just have 1 over Reynolds number in front of that. So this is a one parameter theory of all of fluid mechanics. So when this number is very small, what that means is that the viscosity, or the kinematic viscosity, must be very large. So that means it's a very viscous fluid. So then, as you know from experience, very viscous fluids flow in a steady and predictable way, as shown here, and we call that laminar flow. On the other hand, if the flow velocity is very fast, u is very large, or the viscosity is very small, so the slightest perturbation makes the fluid go into some fluctuating, unpredictable way, then you get fully developed turbulence. Typically, the numbers you can get in the lab might be 10 to the 5, 10 to the 6, 10 to the 7. In a wind tunnel, you might get higher than that. But this is what's called fully developed turbulence. And in the middle is this regime where you have laminar flow coexisting with turbulence flow, as shown here in this wake behind a wind farm. And this number, Reynolds number, is about 2000. This is a very important number. It's important for you because it's roughly about the Reynolds number of the fluid that's flowing through the blood vessels near your heart. And this number is also the number where if you push fluid through a pipe, you get the transition to turbulence. And so why is that transition important? Well, it's important because it can kill you. If you have this transition, as I'll show you, is very jerky and very causes lots of fluctuating forces, and those can rupture blood vessels and give you an aneurysm, and so it's a very dangerous condition. So this is a real interesting question. How do you move this critical Reynolds number around, perhaps to higher Reynolds numbers, so that one doesn't get these transitions and this violent behavior? So fluid mechanics is part of biology. Now, I like to think of fluid mechanics as life and death, biology, if you will. I think of this as being living turbulence. And this part here, I think of as really as the death of turbulence. And so I think of these things as described by these terms. And these two papers here are ones that we contributed, which some of the research I'm going to show you today came from those papers. Okay, so what we have then is at high Reynolds number, I'm going to talk in a minute or two about the cascade of turbulence. At low Reynolds numbers, around about here, we're going to talk in detail about the transition. In this middle regime here, this is a very difficult regime, which is still very hard to explore and is a great source of open problems. And this is where you have turbulence on top of mean flows. In other words, you have a flow that is coming from outside, like the flow that's going backwards over here. And so you have a net flow on top of which is turbulence. And the turbulence actually can create other mean flows that interact with the flow that is coming in And so it's a very complicated process, but it's one that gives rise to the beautiful pictures you might see if you look at, say, the big red spot of Jupiter or any of the other outer planets where you get these zonal bands. Okay, so what I'm going to show you today is that statistical mechanics describes this whole system in the following way, that there's a critical behavior here, and this transition is in fact a second order phase transition. I'm going to show you that fully developed turbulence also behaves like as if it were a phase transition at infinite Reynolds number. So the behavior over here is some kind of crossover that comes from the infinite Reynolds number, something in the same way that a quantum critical point at zero temperature has effects that go to very high temperatures, such as in a high temperature superconductor, for example. And I will try to be explaining what the unifying concepts are and how one can use universality and the normalization group ideas to understand fully developed turbulence from this fixed point and the laminar-turbulent transition from this fixed point. Okay, so what does it mean to solve turbulence? Well, if you asked a physicist in the street, what she would say is, well, of course, what one should understand are the fluctuations in turbulence, because turbulence is all about fluctuations. And so how does one characterize those fluctuations? And so let's talk about where that comes from. And so I'm now going to teach you something very profound about turbulence, which we still cannot derive in any systematic way. So the question is this: what happens when you have a turbulent fluid? And of course, what happens is you have some swirly, twirly thing, which we call an eddy. Hard to define exactly what it is. And those swirly, twirly things break down into smaller twirly, whirly things like this one, which breaks down into smaller ones like this as well. What I'm plotting here on the horizontal axis is inverse length. So this is wave number, if you will. So when I go from here to here, I'm going from large scales to small scales. And I'm going to explain what this thing is in just a minute. But for the moment, I just want you to focus on these swirly, whirly motions that are characteristic of fluid flow. And the key insight that Richardson had in the 1920s and Kolmogorov developed in the 1940s is that this process of spinning off these smaller and smaller eddies is a Hamiltonian process. What that means is it's a process that involves no dissipation. So typically when you see something spinning and then breaking up into smaller and smaller parts, you think it's sort of running out of energy and falling apart. That's not what happens in turbulence. This breaking up is not the failure of turbulence. This is what turbulence actually does. And so this process is just the inertia-driven flow of the fluid. And the idea is that because this is a hypothesis that this is a Hamiltonian process, it's a hypothesis, what it says is that if you input energy at large length scales, which means small wave numbers, then that energy will flow down to smaller and smaller scales through this process of breaking up eddies into smaller and smaller eddies. And we can calculate exactly how the energy is partitioned at different wave numbers by an argument, a very sophisticated argument due to Kolmogorov, which I'm now going to show you. But the basic idea is that because it's Hamiltonian, viscosity won't enter into the equations. So let's see how this comes about. So we should start off by doing dimensional analysis, and we should start every problem by doing dimensional analysis. So what we want to understand is E of k, and E of k is this: it's the energy per unit wave number range. So if I look at this wave number range from here to here, I ask how much kinetic energy is contained within that range. The answer is E of k. So that's what E of k stands for. Okay, well, what does it depend upon? Well, what E of k will depend upon is the wave number itself, which is k. It's going to depend upon the size of the system, which is L. It's going to depend on the kinematic viscosity, which is nu, and it's going to depend on epsilon, and what epsilon is telling you is how vigorously you're stirring the fluid. So you're pumping energy into a fluid when you are exciting it at some large scale and watching energy flow to smaller and smaller scale. The faster you stir it with your hands or whatever you're doing it with, the more energy you are using, and that energy will ultimately be dissipated as Joule heating when at smaller scales. So it has to depend on that as well. So these are the four parameters on which the kinetic energy spectral density can depend. And out of these numbers, we can construct a length scale called the Kolmogorov length scale. That is defined as nu cubed over epsilon to the 1/4. And you can work this out and you can see that this is a length scale. So once you know that, then I can do dimensional analysis and work out what the energy spectrum is in terms of the length scale, and then L and K and nu. And the answer is the formula written down here. It goes as nu squared over eta times some arbitrary function of K, which is inverse length times eta, and K, which is inverse length times L, which is the size of the system. So the size of the system might be the radius of a pipe, if you want to think about a fluid flow through a pipe. Okay, so what one wants to understand is the fluctuations at small length scales. And so small length scales means sending K to infinity. So we're going to take the limit that this parameter K times L goes to infinity. And so then we replace K times L by infinity itself. So there it is. And now this is now a function. This now is just infinity. So now this only depends upon this variable here. And so now this is now a function of only one variable. So now what we're going to ask is, now what happens as we go to larger and larger Reynolds numbers? So larger Reynolds numbers means that the viscosity is getting smaller and smaller. So that means nu is going to 0, and so that means the length scale is going to 0. And so that means that K eta is going to 0. So what we're going to do then is replace K eta by its value at its value 0. And so now we have E of K is nu squared over eta K times a function whose first argument has the value 0 and whose second argument has the value infinity. This f0 infinity is just some number. Let's say it's 17 or something like this. And what we have left is this thing, and if you work it out from the definition of this turns out to be just epsilon to the 2/3 times k to the minus 5/3. So what we've learned from this is that the energy spectrum, the turbulent kinetic energy in the wave number range k to k plus dk is actually a power law. And so this is what it looks like. Here's E of k, here is k. What I've shown you is that it's a power law going as k to the minus 5/3. Now, to do this calculation, we had to take this limit as we're going to small scales and we're going to very high Reynolds numbers. In actual fact, we never go to infinite Reynolds numbers, and so the inertial range ends at very small scales where friction starts to come in, and then the edges no longer spin off other edges in a Hamiltonian way, and so you get dissipation at high wave numbers. And at small wave numbers, that's where you're putting the energy into the system, and so the energy is going like something like k squared or something like that at small wave numbers, and then this is the scale here, where which is roughly the size of the system. So that's our picture, our sketch, our cartoon of what the energy spectrum looks like. And here, just to remind you, is the definition of E of k. It's the kinetic energy, UK, the Fourier transform of the velocity, Fourier component UK squared d by dk, the amount of kinetic energy per unit wave number. Okay, so that's the similarity hypothesis. That's the K is the 5/3 law. That is the most famous result in turbulence. The only thing about it is that it's not correct. So let's see where we went wrong. So we made some interesting arguments here. What we did, let's go back to this. So what we said was we want to take the limit of the system size going to infinity, or if you like, K getting larger and larger, and at the same time the viscosity going to 0, or the Reynolds number going to infinity. And then what we did was we replaced these variables, KL time over here, K eta over here, we replaced them by their actual limiting values, infinity in this case, 0 in this case. But suppose those limits don't actually exist. Okay? So we've assumed that we can just replace K eta going to 0 is the same as K eta equals 0. but it doesn't have to be the same. It doesn't have to be that those limits exist. Let's see how they could break down. Let's not talk about this limit for the moment. Let's talk about actually, no, excuse me, I do want to talk about this limit. I don't want to talk about this limit for the moment. So let's ask, what happens as we take the limit KL goes to infinity, but how could that limit not exist? Well, one way that it might not exist is that the functional form here of this is this, just as written down here, but this function f is now a function of the first argument times this second argument to a power, which I'll call eta. Now, if it goes like that, if that is the actual mathematical form, then as I take the limit KL goes to infinity, this thing is either going to go to infinity if eta is positive, or it's going to go to 0 if eta is negative. So this is an example of a functional form where if I were to take this limiting case, the whole left-hand side would not make any sense. Well, this is a physically observable quantity, so it has to be, this has to be finite. So what that means is we cannot take this limit, literally set at KL equal to infinity. We just have to say that the functional form, asymptotically as KL it becomes large, has this form here. And this, when these limits don't exist, that's called incomplete similarity. And I would recommend for you a wonderful book by Grigory Barenblatt called Similarity, Self-Similarity, and Intermediate Asymptotics, which is full of examples in fluid mechanics and continuum mechanics and other areas of physics where these limiting asymptotics don't exist. It also turns out that the problem of phase transitions is another example where this limit doesn't exist. And we'll talk a little bit about that later. Now, I want to go back to turbulence and ask what happens if this indeed is the behavior. But if this indeed is the behavior, then the 5/3 law is going to be modified. This factor here will then multiply this. And so the scaling will go as k to the minus 5/3 plus something that depends on eta itself. And it depends on k times L. It has to depend on this combination because this whole thing has to be have the dimensions of E of k, and this already does have the dimensions of E of k. This thing is just a number, so this thing has to be dimensionless, and so k and L have to both appear here raised to some power. And this power eta is known as the intermittency exponent. And I'm going to show you later on in these lectures how one can measure it using phase transitions in the normalization group kind of ideas. Okay, so that's a pretty long answer to the question of how do you solve turbulence, and the answer is you study what happens at small length scales and look at the energy spectrum, the kinetic energy in this wave number range, or if you like, the velocity order correlation function. Okay, there's another thing that you might ask. You might say, well, that's fine, I don't care about that, I'm an engineer. And as an engineer, I don't care about what actually is happening at small scales. I want to design a pipeline, or I want to design an automobile, or I want to design an airplane. And I want to know how much friction will that experience as the airplane flies through the air or the car moves through it. And so we want to understand the dissipation. So I'm going to come back to this graph tomorrow, but let me just introduce it for you and just tell you what it shows. So this is the friction factor in pipes. So the idea is this, we'll talk more about this tomorrow. You send fluid going through a pipe and you ask, I want the fluid to go at a certain speed. How much power do I need to expend to push the fluid through the pipe? And that, of course, is a measure of how much friction the fluid experiences as it goes through the pipe. And the answer to that we'll call the friction factor. I'll define it for you tomorrow. It's basically just the pressure drop per unit length normalized by the kinetic energy of the flow. Okay, but that's just this F stands for friction, and here is the Reynolds number, and you can see this is a logarithmic scale, log to base 10, and what this graph shows you, we'll discuss in great detail tomorrow, but you can see that the answer is not simple. That if I have a pipe that is smooth, the friction is smaller than if the pipe is rough. That's the first thing you can see. The other thing you can see, this regime here turns out to be when the fluid is laminar. All of this over here, from here onwards, is the fluid being turbulent. And you can see that the friction factor goes down, then bottoms out, and then goes flat, and eventually becomes independent of Reynolds number. Okay? So these are data, and we're going to try tomorrow to understand the anatomy of this curve. Okay, so that's another answer. So there's another thing you might say as an answer to the question of how do you solve turbulence. You might say, well, those two things are different questions, but maybe they're connected. And one of the big trends in statistical physics and condensed matter physics in general over the last 20, 30 years has been this idea that we should be able to connect different levels of description, different scales. And so one might say, can one predict the dissipation experienced at large scales from the fluctuations at small scales? Because after all, those fluctuations are what is driving the fluid motion that's giving rise to the friction in the first place. And so this is a question. Does the fluctuations determine the friction? And I'm going to show to you that the answer is almost surely yes. And if this is true, which I believe it to be the case, what it says is that small-scale velocity fluctuations determine the dissipation at large scales. So there's a scale interference, and this is very reminiscent of something in statistical mechanics, which you've surely heard about, which is the fluctuation dissipation theorem. Now, the fluctuation dissipation theorem that you learned about, when you were doing Brownian motion in elementary statistical physics, that's a theorem in equilibrium statistical mechanics, but turbulence is very far from equilibrium, and so that's not applicable here. So we have to understand what is the analog of these things. Okay, and one of the things I'm going to show you is that in contrast to the traditional view of fluid mechanics, it's just looking at the equation of motion and not thinking about the statistical physics of it, we're going to see that the friction at large scales really does reflect the nature of the turbulent state at smaller scales. We're going to be able to see that something strange happens at smaller scales that affects at large scales. And the way we're going to probe that is by looking at turbulence in different dimensions, which is again another theme of modern day statistical mechanics. So another way one can try to say, let's try to understand turbulence, is to predict how fluids become turbulent in the first place. And that's what I want to say something about now. So the original experiments in this were done by Reynolds, who defined the eponymous number named after him. And this is the experiment apparatus that he had. He has a pipe, he injects fluid into the pipe, and he varies the speed, and then he sees what happens. And how does he see what happens? Well, what he does is inject ink into the flow, and you can visualize the flow in this way. So these are three pictures taken from his 1883 paper, and as you go down like this, you see higher and higher speeds. So first of all, at low speed, the ink makes just a smooth, regular streak like this. At high Reynolds numbers, after some initial transient, the ink forms these swirly-whirly things, and you get turbulence. But in between, you get the transition to turbulence, and that happens in a very weird way. What happens is the fluid is laminar, then jaggedy and turbulent and irregular, then laminar again, then jaggedy, irregular and turbulent, and so on and so forth. And we call these little patches of turbulence, we call them puffs. Reynolds called them flashes, but we call them puffs. Okay, so the question you might then ask is, well, if this is my picture, over here there's no turbulence. Over here at large Reynolds numbers, there's a lot of turbulence. So I might ask, how much turbulence actually is in a pipe? So here's a pipe, and I can measure, this part is turbulent, this part is laminar, this part is laminar, this part is turbulent, this part is laminar. How much turbulence is in the pipe? Well, here's the answer. The turbulent fraction as a function of Reynolds number is 0 until you get to high enough Reynolds numbers, and then it gradually rises in the way that I've shown you here. These points here are actual data. They're not really for a pipe. They're for an analog system for a pipe, a Couette system. But never mind that. It's the same thing. And this is the way that a fluid becomes turbulent through this variation shown here. So the point is that this transition is not spatially uniform. You get rare, sharp bursts of turbulence interspersed by uniform behavior. Now, because it's spatially structured like that, then we have to understand what is this quantitative description of the transition to turbulence. And it's complicated. Now, one of the things you may notice is if you look at this picture and you compare it to, say, what you may have seen in my book on phase transitions or in the other papers on phase transitions, you'll see that this turbulent fraction as a function of Reynolds number looks like the order parameter, say, in a magnet or whatever, as a function of, say, temperature. So this is reminiscent of a continuous phase transition. And you may also have noticed that when we talk about the energy spectrum at high Reynolds number, this parallel behavior, k to the minus 5/3, says that I have velocity fluctuations. So because E of k is the expectation value of uk times uk squared, the absolute value squared. So it's a velocity correlation function. And as you may know, in continuous phase transitions, you get power law correlated fluctuations. And so it seems that turbulence has a lot to do with phase transitions, and it does. So why is fully developed turbulence hard? So let's answer this question by asking, well, why are phase transitions hard? Okay, so you can read my book, and I assume that most of you have got some sort of basic level of understanding. So I'm not going to go through this in great detail, but the reason that phase transitions are hard is because you have an order parameter, such as the magnetization of the magnet, and the order parameter fluctuates strongly. And here's an example of the order parameter phi, the magnetization of the magnet, let's say, as a function of time. And you can see that these fluctuations are very large fluctuations. Here's the mean value, but in these fluctuations, the order parameter is nearly vanishing and then coming back to its mean value. And in fact, this distribution is a rather noticeably skewed distribution. So it's very non-Gaussian fluctuations, and it's very bursty. Intermittent is the word we use to describe that. Now, if you look at the description of this in terms of thermodynamics, the place we start is the Landau free energy, which is the expansion of the free energy in terms of the order parameter. Now, if you've read my book, you know it's not really the free energy itself, like a Helmholtz free energy or Gibbs free energy. What it really is the free energy you get by coarse grading the system on larger and larger scales. And this is a free energy function now of the order parameter as a function of space that captures all of the critical behavior. Now, the reason that the phase transition problem was hard, and it took people 50, 60 years to solve it, and the person who solved it, Ken Wilson, won the Nobel Prize, is that there's no small parameter in the problem. Okay, so you might say, well, that can't be right, because if I'm looking at critical phenomena, I'm looking near a phase transition, so t minus tc should be a small number. So this little t is going to be a small number of order 10 to the minus 2, 10 to the minus 3, 10 to the minus 4, something like that. So there is a small parameter. So why is it still hard? Well, the reason is this. If you go through and do dimensional analysis and scale the Landau free energy and do all of that, what you find is that once you've done all that, although you've got one parameter here, one parameter here, and one parameter here, which tells you about how the interactions, how the fluctuations interact with each other, you've got three parameters, but in fact, when you rescale them, this one goes to 1, this one goes to 1, and this one goes to this parameter u tilde, which is just this combination over here. And really, then there's only one parameter, just this parameter u naught bar. Now, if you're in greater than 4 dimensions and t is going to 0, then indeed u naught tilde will go to 0, and this will be a small parameter, and you'll just have a free field theory. But if you're in less than 4 dimensions, which is where we are most of the time, then as you take the limit, as you get closer and closer to the critical temperature, actually the interactions between the fluctuations, u naught bar, goes to infinity, and so it becomes infinitely strong. And so there's no usable small parameter in this problem, even though you think that there is a small parameter to start with. Now, when we look at turbulence, we have a similar thing. If you have these strong swirly-whirly things which are interacting, and we describe those by fluctuations in gradients of the velocity field, those fluctuations turn out to be also very non-Gaussian. You can see here, this is a real time series from turbulence, And you can see what's happening is it's not doing much, and then there's a huge burst here, a huge burst here, a little bit over here, and a huge burst over here, and so on and so forth. This does not look like what you would get if you had small fluctuations around some average. It's not like these are not Gaussian fluctuations. Similarly, if I go back to the Navier-Stokes equations, I might say, well, there's a small parameter, because in fully developed turbulence, I let the kinematic viscosity go to 0, or equivalently, the Reynolds number going to infinity. But if I do that, then what happens is that the coefficient of the nonlinear term, which is this one, as I take the viscosity going to 0, this divided by this is getting infinitely large. So the coefficient of the nonlinearity is getting relatively large compared to the viscous term as we get into the large Reynolds number limit. So that means that this parameter never goes away, and so again you have no usable small parameter. So that's why turbulence is hard. So then you might say, well, it is hard, but it's pretty much like critical phenomena. So why don't we just solve it the same way that critical phenomena is solved? And I agree, that is a really good thing to do. So let's just try to remind ourselves, how was critical phenomena solved? Well, back in the in early 1970 and 71 and so on, Ken Wilson wrote a series of papers which developed renormalization group theory. And that was based on Kazanoff's scaling ideas. Now, Kazanoff, actually at my university, the University of Illinois, explained, came up with the idea of the fact that the description of a statistical mechanical system depends on the length scale at which you're looking at it at. He had the idea that interactions, say, between spins vary depending on the scale at which you're looking. And he used that to explain something that this gentleman, Ben Widham, had discovered the previous year, which is data collapse. And we're going to talk about that in a few minutes. So we're going to see, in fact, that Widham discovered that the equation of state of say, a fluid or a magnet falls onto one universal curve. And we're going to see the same thing is true in turbulence. That turbulence does have the same qualitative features as critical phenomena, and indeed exhibits critical phenomena at its onset. Okay, so now let's talk about the transition to turbulence. So this is Werner Heisenberg, who invented quantum mechanics. He also did a PhD thesis before he invented quantum mechanics, and his PhD thesis was on the transition to turbulence. So this is a suitably exalted subject for us to be studying. Now, I showed you earlier on how Mr. Reynolds studied turbulence. Let me now tell you how we study turbulence today. And now I'm going to draw heavily on work by Björn Hoff and collaborators starting about 10 or 12 years ago. So the question is this. We're going to try to measure precisely the transition to turbulence. And the way you do it is, the way you do it is by asking a question that is a different one than the usual one. The question you ask is this. Let's suppose I have a pipe, fluid is going through it, and the fluid is at rest. And then I make a disturbance over here. I just sort of inject a little bit of fluid and that stirs things up. That stirring things up will create one of those flashes or puffs of turbulence. And that puff will then travel down the pipe like this until eventually it comes out the other end. And the question we want to ask is, how long does that puff survive? How long will it live? So it could do this. It could start over here, start going down the pipe, and then eventually vanish and the fluid be laminar, in which case then the flow would come out along the yellow trajectory shown over here. But on the other hand, if the turbulent region lives long enough until it gets to the other end, the turbulence causes there to be increased drag, and that means that the fluid will come out slower, and so therefore it'll follow the red trajectory here. So what we can do is we can ask, we know how fast the fluid is flowing because we are injecting it. We know how far it is from the injection point to the end point. So we can do time of flight measurements. And then we can do this many, many times. And so we can measure the survival probability of turbulence as a function of the flow speed, the Reynolds number, and the time t. And this is what you get. So this phase diagram here has got the Reynolds number along the horizontal axis. And what I'm showing you here is a numerical simulation done by Avila et al., showing you that here is a puff, and the color scale is the turbulence intensity. And this puff will start off like this, and if you watch it, it'll just sit there, moving with the flow, and then eventually it will just sort of disintegrate and evaporate and fade away. And so it's a puff that decays. And so we're going to call this regime a metastable puff regime. So now what you do is you measure the survival probability of this puff as a function of time for different Reynolds numbers. And what you find is this. This is the logarithm of the probability as a function of time. It's a semi-log plot. And the data, as you can see in these early data, they fall on the straight line. So that means that this survival probability is an exponential function of time with a characteristic length scale, a characteristic time scale, and that time scale depends on what the Reynolds number is. And so the time scale, when the Reynolds number is small, is very short. And as I increase the Reynolds number, I get closer to the transition, which I can tell you is around about 2040, 2050, that time scale gets longer and longer. So let's plot what that time scale looks like. So this is the time scale, tau, as a function of Reynolds number here. This is logarithm, this is linear scale. And you can see the data don't fall on a straight line, but curve upwards. If the data fell on a straight line, this would be that the lifetime increases exponentially with Reynolds number. But it doesn't, it increases faster than exponential. And in fact, we're going to see that this is something we call super exponential. Okay, okay, so puff lifetime is an increasing function of Reynolds number.
Nigel, can I just ask the question?
Sure.
So can you explain once more how how exactly, so you start with a laminar flow and you inject a puff at some point in the tube.
Yes.
And then how exactly do you determine the lifetime?
Well, I can't, all I ask is this: did it survive when it got to the end or not? So I work out the survival probability. And then once I know the survival probability, I can write the survival probability. That survival probability is defined by this equation here, because that's the result of the experiment. So that's just an empirical finding that the survival, so we don't measure the time, we just know, did it survive, yes or no. Survival probability means that the lifetime of the turbulence is longer than the time it took to go from here to coming out the other end.
Okay, and you just watch with the light at the end, whether it's okay.
Yep. In the early experiments, you did it just by yes or no. Today, there's more sophisticated ways to measure what is happening at the end, but it's basically the same thing. You're doing a binary measurement at the end, and once you've done many million repetitions of that, you can then work out that probability distribution. And it's a hard experiment to do, because when you have a turbulent fluid, it heats up.
Yeah, so I still have one question. So so as you go close to the transition, isn't it kind of difficult to identify that this is the same puff that you are seeing? Because other puffs might get generated, right?
Well, that's the thing I'm going to come to. So this is one puff. So as you go slightly higher in Reynolds number, now what happens is you get two puffs. So the puff can either decay, or it can actually split into two and sort of kick out a baby puff, and that will grow into a regular puff, and then the two of them will carry on in an independent way. And so you can then ask, well, how long does it take for a puff to split? And you might think to yourself, well, this is what it's going to look like. It's going to look like this. It's going to be that if I'm very high Reynolds number, if I make up a little bit of turbulence, immediately it's going to spread and create the state of turbulence. And as I go to smaller and smaller Reynolds numbers, that should, that time scale should get longer and longer because the puff will sit there and sit there and sit there, and eventually it'll split. So as you get more and more turbulent, it'll want to split faster. And so when you measure it, indeed, the mean time between splitting events gets smaller as you go to larger and larger Reynolds numbers. And you can see that on this semi-log scale, this time scale also is curving upwards. And so it's faster than exponential. So what actually is it doing? Well, if I take the log of the log, that's 2 logarithms, then you get the data fall in these nice straight lines, and you might say where they intersect is where the critical Reynolds number is, and that's typically how we define it. So the idea is below this Reynolds number, the turbulence will eventually go away. If you're above this Reynolds number, the turbulence will eventually fill the pipe because you'll get more and more of these puffs. You'll have a non-zero turbulent fraction, although it won't be 1 until you get to very high Reynolds numbers. So this fact that you get a straight line when you take a double log means that the lifetime, all these time scales are going as e to the Reynolds number. And so this is what we call super exponential scaling. Okay, so let me tell you about the theory for this. So I have no idea how I'm doing for time now because of the mess up with the
you can take half an hour or what, I mean, whatever time.
Great. Yeah, let me do that. I probably won't need to take half an hour, but if I've got that time, then I'll be happy to do that. I can talk slower. All right, so here's the theory for this transition. Let me explain. I'm going to explain to you now where all that comes from, and it's really, really unusual and strange. So let's think about the logic of modeling phase transitions. So this is how we do it in phase transitions. Let's start off with a magnet. So the lowest level of description in a magnet, what you have is your electronic structure. You have your band structure, you have your electrons moving around, they have spins and so on, and you can make a very detailed model of, say, a turbulent for magnetism or something like this. Well, of course, that's exceedingly complicated to understand. So what one does is one says, well, let's just worry about the spin degrees of freedom, and let's ask how electrons interact and how their spins interact through exchange interactions and so on. And you get a model called the Ising model, which is just a model of spins interacting. It's a quantum mechanical model, but you say, well, that's too hard to solve, so let's make it classical. So now you've got a classical model, and it's a classical model of spins, and that's still too hard to solve unless you're in 2 dimensions, and there's no external magnetic field, and your name happens to be Onsager. In that case, it can be solved, and that's one of the great tour de forces of mathematical physics in the 20th century. Okay, so the 2-dimensional classical Ising model can be solved in no external field, otherwise nothing can be done. So then you say, well, let's simplify it and let's write down our coarse-grained theory, which is Landau theory, which is the one I showed you some time ago. And then from Landau theory, one can turn the crank of the normalization group and work out the universality class. And what that means is the following, and we're going to see these diagrams a couple more times in these lectures. As we go down in temperature, the order parameter, the magnetization, rises from 0 in the way I'm showing you here, and it does it with some parallel beta, and the way that the behavior here is controlled by weak long wavelength modes. The long wavelength fluctuations, they're weak because the magnitude of the magnetization is very small, and we'll talk about the data collapse later. Okay, so just remember this picture for now. Let me also point out that if you look at the external magnetic field and temperature in that axis here, in 0 external field, you have this second order phase transition below TC, as shown here. And if I go across this line below TC from a negative external field to a positive one, there's a first order phase transition. So that's the phase transition of an applet. And we can understand that very well from this picture. Now in turbulence, the lowest level of description that we have is, say, kinetic theory, particles bouncing around in a box, which is how we started this lecture. If we then say, well, I don't care about that so much, I want to coarse grain and just look at the velocity field that I get, then that would be the Navier-Stokes equations. But the question I want to ask now then is, well, that's great, but it doesn't tell you about the phase transition. The Ising model tells you about all of magnetism, but if I'm interested in the phase transition, all I really need is looking at the behavior near the critical point, and that's the Landau theory. So the question that we should be asking ourselves is, what is the analog of Landau theory for the laminar turbulence transition? And what is the analog of the renormalization group universality class? Okay, so now I'm going to show you how we figured out this. And the way we're going to do it is instructive, because we're going to use numerical methods as a way to build a model. So we're going to use the numerics, not to calculate something exactly, but to calculate something in a qualitative way. And then we can, once we get the idea of what's going on, then we can use those insights. So this is what I want to do now, is take a digression and how we should use computer simulation as a tool for making discoveries. Okay, so this is, the slide can be called computer simulation, and what I like to call the curse of excessive realism. Okay, so what is the curse of excessive realism? Well, let's go back to Leo Kadanoff. So Leo Kadanoff was in fact a friend of mine for many years. He died a few years ago. So it's quite fitting to celebrate his memory in this talk, particularly since he not only really had the pivotal insights on the normalization group theory and phase transitions, but also many important works in turbulence. Now, one of the things that he worked on when he wasn't working on phase transitions and critical phenomena and turbulence was he worked on urban planning. And this was in the late 1960s, after he left the University of Illinois. People at that time had access to computers, and they started to make computer models of urban change. Literally, how do you plan livable zones inside a city? And this person, Jay Forrester of MIT, had developed such a computer model, and Leo Kadanoff is writing here, this is a quote from one of his books, that he did not like the social policy that came out of these computer simulations. So what did Kadanoff do? He decided to use computer simulations that reached conclusions which were more to his liking, more to his sense of social justice and so on. And what Kadanoff says is that we discovered that if we didn't change the model, we could still reach opposite conclusions from that of the MIT group. And so what he says is, we went in to build other models, which more accurately recorded our own prejudices and points of views. And after a while, the point we had made began to sink in. If these models really represented little more than we could say in words, why not just leave out the computer? In other words, what Kadanoff was saying was, computer simulation is garbage in, garbage out. And he says, this seemed, applications of computer models to social sciences to him seemed a rather pointless endeavor, and so he moved away from urban studies and back towards phase transitions and chaos and other things like this. And this is where you can read about this if you're interested in a collection of his essays and famous papers. So the moral of this story is interesting. There's two ways that you can model nature. One which I'll call excessive realism, and one which I'll call minimal models. So excessive realism says everything is computed as accurately as possible with many levels of description and fitting parameters. You really want to get everything right. Going back to our picture of the magnet, it means I don't just want the phase transition behavior, I want the whole enchilada. I want the band structure, I want everything, I want to know the electron-phonal interactions, everything that there possibly could be. That's what we'll call excessive realism. Minimal models is the exact opposite case. Everything you compute is computed as sloppily as possible, with as few levels of description as possible, and as few fitting parameters as possible. The ideal is to have a model with no adjustable parameters. or maybe one adjustment parameter if you want to be generous. And the great thing is that you can do that. We'll call these things minimal models, and where they come from is essentially renormalization group considerations. So what's the use of these things? Well, excessive realism is good if you want to compute to get numerical information that verbal arguments on their own cannot address. You really want to know the band gap of silicon, and you want to know it exactly to 5 decimal places because you're building the chip that powers this computer. Well, okay, so then you really need the numbers. If you just want to find out what is the phase diagram of, say, turbulence, or the phase diagram of a magnet, or whatever, well, that's an example of something which is emergent, and you can compute that qualitative information without needing to include all the information. And that's what we'll call a minimal model. So let me give you an example of that. The one I like to make is this. Well, what is an emergent phenomenon? Well, I'd say that emergence is always accompanied by the presence of a rigidity, some kind of stiffness that tells you how you've created a new state of order, and that order then resists change, and therefore you get some kind of rigidity. So, for example, take a fluid and a solid. I asked you what is the difference between a fluid and a solid. You would probably say, well, in a fluid, the atoms move around. In a crystal, the atoms all sit in their lattice positions, and so we should look at the Bragg peaks, and that would tell me what is a crystal, what kind of solid. Of course, you can have disordered solids where they don't have Bragg peaks, but the real distinguishing feature of a crystal is, or of a solid, is not that the atoms are still, but and stuck in place, but that there is a stiffness, there's a non-zero shear modulus. You can push a solid, you can't push a liquid. And so this shear modulus is an example of an emergent phenomenon, and you can compute that using minimal models. Okay, so what we're going to do now is we're going to apply this philosophy to study turbulence. So what we're going to do is simulate it precisely using state-of-the-art methods. I'm not going to go through how we did that, but we didn't write the code we used. We use a standard code that is widely used by people. And then what we are looking for are the presence of generic long wavelength behavior indicative of a phase transition. There are 2 modes that are important near the laminar-turbulent phase transition. So one of those is the mode we're actually interested in, which is turbulence itself, acting at small length scales shown in green here. These are small scale fluctuations. But what we also found was a very weak mode that azimuthal, as shown in this picture here, and here you can see this mode actually, it's time dependent and it's radial dependent. And this mode is, we call it a zonal flow for technical reasons, which I'm not going to go into great detail about. It's a mode that is independent of Z, the direction along the axis of a pipe. So it's a translationally invariant mode. It's a very long wavelength mode. And what it does is it shears the turbulence. So we measured the energy in this mode, and we measured the energy in the turbulence. And what we discovered as a function of time was that these modes oscillate, and they oscillate out of phase. Energy is going into the turbulence from the zonal flow, and then from the turbulence back into the zonal flow, and these things go back and forth like that, as shown here. What's happening here is the following: the turbulent fluctuations have some anisotropy, they're random fluctuations, but what that does is that fluctuation drives a mode, this zonal flow mode, that goes in the azimuthal direction and shears the turbulence. And the reason that we know that is that we can take the Navier-Stokes equations and average them, and I'm not going to go through the algebra for that, but it's in most textbooks like Polk's, for example. And what you will find after some calculation direction depends on the velocity fluctuations in the theta direction, the azimuthal direction, and radial direction dotted together like this. So this is something called the Reynolds tensor. And this thing here, the radial gradient of this, is driving this flow. So the physics of this is very simple, that the turbulence is creating anisotropic fluctuations that cause jets of fluid to sort of squirt out, go down the sides of the pipe, create this flow that is shearing the turbulence and making it more isotropic. So what's happening is you have turbulence, which is by definition fluctuating and has anisotropic snapshots, creates this zonal flow. That zonal flow then shears the turbulence. That makes this term the turbulence be more isotropic, and so therefore this term goes to zero. And when this term goes to zero, then the zonal flow goes to zero. So then that stops the zonal flow from shearing the turbulence, and so the turbulence then starts to rise again. And so you get these oscillations, which are reminiscent of what happens in population biology, where you get predator-prey oscillations. So let's talk about that. So here's a predator, and here's a prey. What's happening is something is a fluctuating population cycle, as shown here. What's happening is this: the predators start eating the prey, the bunny rabbit in this particular case, and then they soon run out of food. So the prey population goes down, and so the predator population goes down. But once the predator population goes down, then the prey can now make babies and they won't get eaten, and so the prey population will go up, and because there's more food, then the wolf population will go up. And so you get these alternating cycles of predator and prey, just like you get these alternating cycles of turbulence and zonal flow. So that tells us that our qualitative picture of turbulence is, near the transition at least, has got these two long wavelength modes, and they behave like a predator and prey in an ecosystem. So let's see how we model those. So what we do is we say, as statistical mechanicians, not as ecologists, but as statistical mechanicians, what we say is, well, I've got the predator and the prey. When a predator, red, meets the prey, they eat it, and then the predator gets energy, and that uses the energy to live and to make baby predators. So what that says is, if a predator meets a prey, that's equivalent to A plus B going to A plus A, a chemical reaction. But this now is a stochastic process with some predation probability P. And so you can now simulate a population of predators and prey following these laws of interaction. This is a prey at an empty site or food having a birth rate B and giving two prey. This is prey competing for scarce resources, and this is just death. And if you then follow the stochastic simulation of this, you will get these oscillations of, say, the predator. And if you try to write this down, by the way, in the way that an ecologist would, you will not get oscillations that are persistent. You will just follow this mean field line here, which clearly is wrong, is not giving you these persistent population cycles. The reason why the stochastic behavior is important is something I'm not going to have time to get. What we learned is that the turbulence acts like a prey, and the zonal flow suppresses the turbulence, so it acts as a predator. So what I'm showing you here is a dictionary of diagrams that tells you how zonal flow and turbulence interact, and a dictionary to map these diagrams of the interactions of zonal flow and turbulence into the population biology of predator and prey. So let's talk about this. So the wiggly line represents turbulence, the solid line represents a zonal flow. And actually these are real Feynman diagrams. One can take the Navier-Stokes equations, write them down as stochastic equations, and work out the Feynman rules and the way that one can write these things down using field theory. And I don't want to take the time to do that. It would take quite a few lectures to explain it if you don't already know it, and you don't really need to know it in order to understand what I'm going to teach you next. But the thing you do need to know is that, remember that Navier-Stokes equations had a u dot grad u term. I told you that they were quadratic. So that means that every vertex, every line will split into two other lines. So all these vertices here are three vertices because of that. nonlinear quadratic nonlinearity. Okay, so what does this diagram tell you? This says zonal flow and turbulence meet, and when something happens, the turbulence disappears and I get more zonal flow. So if I write this interaction down in predator-prey language, it says A plus B goes to A plus A. A plus B goes to A plus A. And that's what this reaction is over here. And you can do the same thing for all of these things. And this actually then describes the statistical mechanics of a predator-prey ecosystem. So you say, well, that's weird. That says that a predator-prey should have a phase transition, which is like the phase transition in turbulence. So does it? Well, yeah, actually it does. So here's how you can see that. So the analog of Reynolds number, which is the picture I've shown you before, is the prey birth rate. So think about it like this. Let's suppose the sheep, or the bunny, whatever it was, make babies very, very infrequently. And the predators will eat them all, and then the prey will just not have time to make any babies, and so they'll die out. On the other hand, if the prey make lots of babies, you know, one baby rabbit every 15 minutes, let's say, okay, obviously ridiculous, but if that happened, well then of course the wolves would not be able to eat the rabbits fast enough to kill them all, and so you get a coexistence of both the predator and the prey. And so that tells you that the Reynolds number is analogous to the prey birth rate. So if the prey birth rate is too small, everything dies out. You only have nutrient left. That's the laminar state. If, on the other hand, you have a very high birth rate, well, then you'll have lots of prey. And in between, you'll have this regime, just like you have a regime of coexisting laminar and turbulence, laminar, turbulence, turbulence, laminar, turbulence, or just laminar and turbulence over here. So you can have the same thing in populations. So this is a picture of a domain where you can have an ecosystem, predator and prey. The blue is the prey. The yellow is the predator, yep, that's right. And what's happening here is if you start up with a well-mixed population, actually I said the wrong way. I apologize. The yellow is the prey and the blue is the predator. These things are traveling waves moving in this direction over here. And so what happens, you start up with a patch of turbulence and it will spontaneously break into the spatial structure. And then over here for high birth rate, you actually get these traveling waves. So these are just traveling bands of predators and preys moving through the ecosystem, exactly like what happens in turbulence. Okay, so let's have a look at the world lines of these things. This is space, and this is time, and the color scale is the intensity of turbulence. This is space, this is time, and the color scale is how much prey you have. And you can see that in both these cases, you get, in the regime which I called the spatio-temporal intensity regime, what you see is that a region of, let's go over here, a region of turbulence goes along in time and then suddenly splits into two regions of turbulence, two puffs, and then these puffs split into two and so on. And the same thing is over here. I have a region of turbulence which eventually splits into two, and that splits into two, and so on and so forth. And so we're starting to see that we're getting the phenomenology of turbulence just from this ludicrously simple model, which knows nothing at all about the Navier-Stokes equation. So then you say, well, okay, this is quite surprising. I've got a predator-prey model that came from population biology. It seems to describe something about the active modes of the turbulence transition. Okay, remember that super exponential behavior I showed you at the beginning? Why don't we measure the statistics of the extinction time, how long this little patch of population will take to decay? And why don't I measure the time between these splitting events? And I'll measure that in the ecosystem analog, and we already know the answer for turbulence. So you go ahead and do that. And this is what you see. Which one is turbulence? This one. This is the turbulence one that I showed you before. Lifetime increasing as of the decay, and then the splitting time decreasing as you go to higher Reynolds numbers. Here is the pre-birth rate, here is the lifetime, this is again a logarithmic scale, and you see this super exponential behavior at the transition between a living coexisting predator-prey ecosystem and one which has no creatures alive in it at all. So what I've just shown you is that the extinction transition in ecology is the same as the death of turbulence, the extinction of turbulence. These two things are in the same universality class. It's really amazing. It's really amazing that you see this connection between something in biology, something in fluid mechanics. Now, what do we really want to know? We want to know what is the universality class of turbulence. And what I've shown you so far is if you start off with turbulence near the phase transition, the laminar-turbulent transition, you get a kind of two-fluid model, which looks like a predator-prey ecosystem. So what I'm going to do in the last few minutes is I'm going to show you that this universality class is directed percolation, a model of statistical mechanics. And what I'll be able to do today is I'll explain what directed percolation is, and I probably won't get through all of the details of how to prove this, and we'll do that in tomorrow's lecture. So let's get started then on this last part of this isomorphism diagram. So what do we mean by directed percolation? So directed percolation is the following computer game. You start off with a bunch of lattice sites, and then you say, let them be either occupied or not occupied. If they're occupied, we'll color them red. And then we say, let's put a pathway between sites with probability P, and probability 1 minus P, there is no pathway. And then the idea is this: start off with a bunch of active sites at the top here, and then when I go forward in time, so time is going in this direction, some of these sites will get occupied as the particles hop from here to here to here to here, and so on and so forth. Excuse me. And you can think of this as being the following. This could be a porous medium, like a rock, or it could be a coffee granule in your coffee percolator. And what you're trying to do is dripping water through the coffee percolator, and the coffee is making its way through, eventually coming out to the other side. Now, your goal is to create the perfect cup of coffee. Your goal is to have the water go through the coffee granules and take as long as possible so you get the nice, strong coffee flavor. So think about what would happen. If this probability of finding a path is very high, then the water will very quickly just flow through this and come out the other end at the bottom, and you'll get a very weak cup of coffee. If, on the other hand, this probability P is very small, so it's very hard to find a path that goes all the way through the system, as shown here, then the water won't be able to flow through at all. You won't get any coffee at all. So the just right cup of coffee is the one where it just about manages to find a path through the system. And I'm going to show you that that is a phase transition. Now, the other thing I want to show you is I look at these pictures over here of possible trajectories of water flowing through this porous medium, so the coffee granules. Any picture that I want to make here is composed of 4 basic moves. So in these pictures here, this is time t, and then this bottom picture is time t plus 1, the next time step. So what can happen is I can have this site be occupied, and then the next site, there's no path from here to here, and so this site stays empty. Or I could have it like this. This site can percolate through to both this one and to this one. We'll call that decoagulation. Or this site cannot hop to this one, but it can hop to the one diagonally. We'll call that diffusion. And lastly, you can have coagulation. Both of these occupied sites end up occupying this site over here, and this one stays empty. So those are the 4 basic processes, and any graph you can make here, any trajectory, can be composed of all of these. So what does the phase diagram look like? Well, the phase diagram looks like this. This over here is when it's very easy to get through, so you get a very weak cup of coffee. This is when it's impossible for the water to get through. And then this is the perfect cup of coffee. This is when the percolation probability P is just the right number, so that you can just about get through to the other side. And if you look at long time, how many sites here are occupied? At this critical value P, PC, it's very few. Way above the transition, there's virtually all of the sites are occupied. So this is in fact a second order phase transition with critical exponents. All right. So what I'm going to show you now is that we can think of turbulence, the decay of turbulence, as being like directed percolation in 3+1 dimensions. And I'm going to just go through this very quickly and show you this, and then we'll quit for today. So let me go back to here. So imagine that the green squares, the green pixels, are little regions inside a pipe. And if they're turbulent, they're green. If they're laminar, they're transparent or blue. And this is, you can think of this as being in one dimension. This would be like the following picture. Here is a line of sites that are occupied. Here is time. The percolation process is I find my way through and then eventually I stop. I find my way through and eventually I stop. And here is the longest path. And what you can see here is that the lifetime of turbulence is that the clock is starting now and we're waiting until the very last pixel has emptied. In other words, what we're looking at is the longest line here. This point here is the last pixel to survive. And so the lifetime is related to this longest trajectory. Okay, so if I look at the statistics of the longest trajectory, they look also like what happens in turbulence. This is the logarithm of the longest percolation path. And again, you can see you get this upward curvature on this semi-log plot showing the super exponential behavior. Okay, so where does the super exponential behavior come from? Well, I'm now going to make a connection to a branch of statistics that I could spend a whole lecture just talking about about these branches of statistics, and that is extreme value statistics. So what I want to know is, what is the statistics of this longest percolation path? So the longest percolation path is the maximum among all of these possible paths here. So think about it like this. Here I've got a bunch of occupied sites, they're seeds. If I follow each site downwards, this one stops over here. This one percolates through to here and then stops. This one, something like this, who knows? So I can think of this as a bunch of independent seeds, and I'm looking at the percolation process amongst these independent random paths. Now what I'm interested in is the probability distribution of the lifetime, and that's the probability distribution of the longest path. Now what is that going to be? Well, you're definitely aware of the central limit theorem. So the central limit theorem says, if I take a bunch of random variables, add them together, and ask, what is the probability distribution of the sum of those random variables? The answer is I get a Gaussian. That's the central limit theorem. So the extreme value statistic says, I don't want to take the average value of these random variables. I want to take the maximum value. And that's different. That has different statistics. You can work it out, and in fact, you can work it out by renormalization group theory. And when you do that, what you find is that the cumulative distribution of this maximum of a bunch of random variables has this functional form e to the minus y, a super exponential form. This, in fact, the central limit theorem has one fixed point, the usual central limit theorem of the Levy stable distributions. The extreme value statistics has three fixed points corresponding to this distribution, sometimes called the Fisher-Tippett-Gumbel distribution. And this is the one that concerns us. This double exponential for the lifetime of the longest path is the fundamental reason why you get the super exponential behavior. Okay, I think I will start by showing you how the predator-prey ecosystem maps into directed percolation. So let's stop there and I'll take some more questions.
Thanks, Nigel. So I think, so Rama, you had a question, right?
Yes, I have a question for you. In this pipe flow, like how special is it that it should be pipe flow? Like this predator-prey thing, is it generalizable to any turbulence, and does it have to be shear turbulence?
So it does have to be shear turbulence. So at the moment, the only thing we know is that this description applies for pipes, although we suspect it applies to channel flow as well, and to couette flow. So in other words, shear turbulence. The most important thing is that you have a subcritical transition. In other words, the laminar state is an absorbing state. So this wouldn't apply to, say, a supercritical transition to turbulence, like you might use in convection, for example. Or Rayleigh-Bernard, yes, exactly. And if you, in fact, if you have Taylor, somebody's microphone. If you have Taylor-Correct flow, depending on which direction the cylinders rotate. So if you have the outer cylinder rotating and the inner one stationary, then you get a shear flow, and this picture applies. If it's not that way, then you can get a supercritical transition to turbulence. So this picture really only applies in that case. Did I answer your question?
Yeah, thank you.
So the interesting question, one thing before the next question, the thing that we're currently trying to understand is how this works in dimensions greater than one. How it works in, say, two-dimensional flows, like a plain Poisson flow or something like that. So that's something we're working on, but we don't know the answer yet. But what we do know is that it is directed percolation in such flows. Okay, somebody else has another question?
Mitesh, you had a question. Mitesh, I see your hand raised.
Hello, am I audible?
Yeah. Yes, we can hear you, Amitesh.
Yeah, so hello, sir. Actually, in the beginning of the talk, while speaking about Kolmogorov spectra and the intermittency exponent, you mentioned that those small-scale statistics are somehow connected to your large-scale observables. For example, this large-scale intermittency that you see in the transition to turbulence. But so how does it connect to the small-scale intermittency that is observed in those intermittency exponents? So is there a direct answer to that, or is it something else that
I will show you tomorrow, not to do with the transition, but to do with the fully developed turbulence. I will show you how the intermittency comes in. So that's a long story. We'll get to it tomorrow.
All right. Thank you.
Sure.
Abhishek.
Hello, am I audible?
Yes, I can hear you.
Yeah, I had one question about the zonal flow. Is the zonal flow laminar?
It is. That's an interesting question. It's kind of laminar, yes.
So
but it's not.
Sorry.
It's not really correct to say it's laminar, in the sense. Let me find the picture. It's a mean flow, so in that sense, it's laminar. But the difference is that it's a k equals 0 mode. So yes, it's long wavelength, and it's not a small scale fluctuating mode like turbulence is.
So is it intriguing that almost the mean flow annihilates completely fluctuating flow? From a completely laminar thing, a mean flow emerges and a completely turbulent.
Yes. It's great questions you're asking. Let me go back to one of my early slides. This is the thing, this thing here, this is what I wanted to show you. So imagine, so one thing I want to stress is that if you've seen turbulence in other places, people often say, well, I can write down Navier-Stokes equations, I can put some stochastic noise on the right side, I can do the thing in periodic boundary conditions, make a homogeneous isotropic, and try to make a model of turbulence like that. I think it's completely the wrong thing to do, because the way that turbulence is really generated in a lab is you just have a mean flow that then turns into turbulence as a result of, say, an interaction with a boundary or something like this. And so I think that the behavior of turbulence when there's a mean flow is very different from the behavior when you're just forcing it in some way to try to make it do fluctuations. Now, what you said is exactly right, but it's not at all obvious. What happens is that the turbulence itself creates mean flows that can self-regulate it. And where that's super important is in plasma fusion. If you're trying to make a tokamak, then your big problem is you're trying to make the drift wave going around the tokamak. I'll show you a picture of that tomorrow. And the zonal flow actually is induced around the outside and contains the turbulence and stops the plasma from hitting walls and destroying the plasma fusion. So the point is that turbulence itself can generate mean flows, and those mean flows, those emergent mean flows, interact with the imposed mean flow. And how to compute that process self-consistently, not just turbulence creating mean flow, but the mean flow then acting back on the turbulence, which is what we're doing here and causing these predator oscillations. So that's what makes this problem very, very difficult. And so we're solving it by stat-mech over here. In this regime, where you have, say, a planetary zonal flow, say like the jet stream on the Earth or the bands of Jupiter and Saturn, it's very, very hard to calculate those things.
I had one more speculative question. Can I ask that?
Of course.
This zonal flow and turbulence coming out of laminar flow looks a bit like this deconfinement transitions in some of the parton theories that condensed matter people do. In this solid state physics people do. Would you comment on that? Is it very different or is it similar? Because it is almost like these two kinds of excitations were confined in the laminar phase, and then they can deconfine and they can again get annihilated together into the vacuum. It looks very similar to that. And then there is a fully developed turbulent phase where they are completely deconfined in a way.
Yeah, I'm not sure I understand. You're trying to say that this is analogous to what? Which kinds of transition in condensed matter physics?
These deconfinement phase transitions, where
okay.
Yeah.
Right.
For example, even in the VKT phase, there is no vortex anti-vortex.
Right.
And then they emerge from the vacuum, and eventually they can deconfine to become fully. Yeah. It looks very similar. This is.
I think it is similar, but those transitions are not. Those are equilibrium transitions, so they're not in the directed percolation universality class. So here, the difference is that here we have no detailed balance. So the description would not be the same as those transitions. Those transitions are more like Kosterlitz-Thours transitions or something like this, I guess. So the fact there's no detailed balance, reflecting the fact that this is out of equilibrium, is why you get a theory, which is, if you wrote it down as a field theory, it would be a non-Hermitian field theory. And we'll talk about that next time.
So Ritarbrata had a question. Yeah, please go ahead.
Yes. Am I audible?
Yes, yeah. I can hear you.
Yes. Hi. Thanks for the talk. So I had a question previously, but after hearing your the zonal and turbulence answer, I had a second question. So if it's okay with your organizer, I will ask the second question first. Yeah. So the second question is about when you were talking about the turbulence coming from the zonal flow, and then the zonal flow getting feedback from the turbulent fluctuations, and again, so is it representative of the self-sustaining process or the the Fabian-Wallach process and
Yeah,
the wave vortex
it's
interaction?
well, it's not the same thing because the direction of the flow is different. So here the zonal flow is in the orthogonal direction, whereas in the self-sustaining process, it's still in the streamwise direction. So I think I have some slides on this for tomorrow. But I can answer your question by showing you that slide. Let me do that. You're obviously a very advanced person, so you know about things like the Wallach self-sustaining process. So what I'm talking about up to now has been really one puff, and I'm ignoring puff interactions. I'm just looking inside here, roughly where my pointer is, and ignoring things out here and ignoring things out here. So that's what we've talked about so far. But that's not really correct, because actually you have multiple puffs, and and what causes the shape are the streamwise shearings, the shear flow in the streamwise direction. So what's happening here is inside the turbulent puff, the velocity profile is very flat, and then gradually it becomes more and more parabolic as you get down to here. But once you have a parabolic profile, you've got a large shear which can be used to drive the turbulence. When the profile is flat behind here, then there's no energy, there's no shear energy, no shear gradient energy available to drive turbulence. And so that's why you get these alternating turbulence and laminar patches, and actually that's something that's been described in a very nice analogy by Dwight Barkley, and relating this to properties of excitable media like the Fitzy-Nagumo equations of a nerve fiber. So what you can do is now you can couple these regions by putting in the streamwise interactions, which does make it something like a little bit like the self-sustaining process. And when you do that, then this predator-prey interaction gives you a full description of the whole phase diagram, including puffs, slugs, and things like this, which I'll talk about next time. So there is a connection, in my view, yes. And that relates to a level of description of the transition to turbulence, which I'm not talking about, which is the sort of very small-scale dynamical systems picture of spatial solutions and how they underlie what we're seeing in the statistical mechanics. So that's a long, rambling answer to your question, but hopefully that connected the dots for you.
Yes, it's illuminating. Thank you. And the other small question is about the fluctuations in the predator-prey dynamics as compared to the turbulent fluctuations. Are they exact? So, is there a parameter by which you can compare the intermittency in one to the intermittency in the other, or the non-Gaussianness of the fluctuations in the predator-prey to the pipe flow turbulence? And does this fluctuation have any role to play in this kind of an equivalence or a map that you draw between the two?
So
Or the quality of
let's be careful with the language. So I would like to insist on using intermittency just for fully developed turbulence.
Okay.
And you might want to say, well, what about anomalous dimensions characterizing, say, critical exponents of a phase transition? So let's talk about that. So if you're talking about the anomalous dimensions or the critical exponents of this transition, the predator-prey transition, are exactly the same as those of the turbulent transition. And I'll show you that next time. They fall into exactly the same universality class, and we know them exactly. And I'll show you data where they've been measured experimentally, and they fit exactly to the predictions.
Okay, thank you.
Okay.
This one last question, Arnav.
Hello, am I audible?
Yes, I can hear you.
Thank you for this nice talk. So what I want to know is like, you mentioned some similarities or mapping between the onset of turbulence and the predator-prey model or the DP, the directed population. So is it possible to draw similar kind of similarities or mapping when the coefficient of the nonlinear term of the Navier-Stokes equation is not unity? In other words, if the Galilean invariance is not there?
That's an interesting question. Let me think about that. Well, there's all sorts of things that happen when you don't have, when the system is no longer Galilean invariant. But where did I use that in any of this?
So in
So I don't know, but I think it's different. And the reason is this: I did use the Galilean invariants, right? Because when I identified the modes, I identified them using a computer to discover what those modes were. And in that computer simulation, I used Galilean invariants. I had the coefficient of the nonlinearity to be 1. So I don't know if the phenomenon, if I put a lambda in front of it or something, and lambda is not equal to 1, I'm not sure what the actual behavior is. Do you happen to know?
What I mean is like, so it means that the Galilean invariance is critical. You think that it may be critical to this mapping, right? That between these mappings between onset of turbulence and DP. Okay.
Yes.
So I ask this because so there is something, it's just active systems. So when we have this Vijek fluid and all, they wrote similar like Navier-Stokes like equation, but without the Galilean invariance, and there also they predict some kind of turbulent behavior, but it seems completely different from what you mentioned today, the classical turbulence thing. So in this context, actually, I asked this question.
Yeah. So say again, which systems are you thinking of which have the different coefficient for U dot grad U? Which system is it that you're thinking of?
Okay. So this is the Navier-Stokes kind of equation. So it is. You mentioned today there's this passive fluid, but this Vijek and then Sriram and.
So this is active matter model.
Yes. So John Toner.
Toner 2 and all that thing.
Yeah. So in this context, I'm just asking this: if I lose the Galilean invariance at some point in time, then whether these kind of similarities that you mentioned, it is very they are very well, at least to some extent, studied model in the statistical mechanics. So we have some kind of known results in these DP or predator-prey models. So we can utilize them to understand the active systems as well, if there is any mapping if there is any such mapping. But for that,
it's a really nice question, and it's one I haven't thought about. So the problem, there is a connection, I think, because originally, well, here's what I want to say. I don't think I'm the answer to the question. I'll see if I can think of an answer for you for tomorrow. But the sort of flocking transition was originally thought to be a second order transition, and then people discovered that if you went to big systems, actually this transition was more like a liquid gas transition, right? It's not really a continuous transition in the same way that we have here. But on the other hand, this transition, the turbulent one, is also kind of, you do have these coexisting regions of turbulence, regions of laminar, regions of turbulence, regions of laminar. And in the flocking transitions, you do get these traveling bands that move through the system near the onset. So maybe there's a connection in that way. Does that make any sense?
Okay, so I think that's there are no other questions. So maybe we stop for today. So then, thanks again, and see you all tomorrow at 8 in the morning.
Okay, great. Okay.
See you. Bye.
Bye-bye.